Welcome back to Module 6 of an Introduction to Engineering Vibrations. Today's learning outcome is to develop equivalent spring constants for real-world beam structures. Last time we did an axially loaded member and a torsionally loaded structural member. Today we're going to do beam structures. And so here's our equivalent spring constant, or equivalent spring, ideal spring. And let's look at a simply supported beam, where we have two supports, a pin and a roller on either end, and we've got a force P being applied at the center. It's a concentrated load. And we find that the deflection equals PL cubed over 48 EI. And I'd like to refer again to an earlier course that I did in Mechanics of Materials to show you how I developed that deflection. So as a final slide here, we have the maximum deflection of a simply supported beam with a concentrated load at the center is PL cubed over 48 EI, and we see that it occurs at the center of the beam. So again, we see that the notation is different between our linear spring in this course and the Mechanics of Materials course. The force P is now F, and the deflection is delta instead of Y. And so I can set up and show the force from this spring equal to 48 EI over L cubed. If I compare that to F equals K delta, I see that the equivalent spring constant for this simply supported beam is 48 EI over L cubed. Let's do an example together now. And here's our system. We have a spring K1 here at the top. We have just a rigid bar that I'm going to deflect down delta. And then I have a simply supported beam structure connected to another spring K3. Since the beam structure and this K3 spring have the same displacement, what kind of equivalent spring? Is this parallel or in series? And what you should have said to yourself is this is in parallel. Again, because they have the same displacement. And so we've got the K equivalent 1 for this portion of the system equals the 48 EI over L cubed, and then plus the spring force in the K3 spring, which is plus K3. And now I have this new spring here that's equal to K equivalent 1. And now it is in parallel with K1. And so again, we're going to add those together. So I have K equivalent total equals K equivalent 1 plus K1. And so K equivalent total for this system is equal to K1 plus 48 EI over L cubed plus K3. And that's the answer to that worksheet. And so I have another example for you to do. And this is a sack of cement that's being dropped from a height of 3.49 feet on a simply supported center of a beam. We're going to assume that the mass of the beam may be neglected as compared to the sack of cement. And I want you to estimate the maximum deflection of the center of the beam. And I've given you some beam properties. I've given you Young's modulus. I've given you the area moment of inertia. And I've given you L, the length of the beam. And as I say here, I give you a hint that you're going to use work energy principles from my course, Engineering Systems in Motion, Dynamics of Particles and Bodies in Two-Dimensional Motion. And I also have put up the solution in this module. And so, in summary, this was another module where we looked at coming up with equivalent spring constants, this time for real-world beam structures.